Henkel transform of derivatives. Henkel transform of d squared f by dx square plus 1 by x df by dx, where p is the root of the equation Jn of pa, which is equal to 0. We'll see the solution. We know that the definition of Henkel transformation Hn of f of x, which is equal to integral 0 to a f of x into Jn of px dx. Therefore, Hn of d square f by dx square plus 1 by x df by dx, which is equal to integral 0 to a d square f by dx square plus 1 by x df by dx into Jn of px dx. Just we are replacing f of x by d square f by dx square plus 1 by x into df by dx. That is Hn of d square f by dx square plus 1 by x df by dx, which is equal to integral 0 to a d square f by dx square x into Jn of px dx plus integral 0 to a df by dx into Jn of px dx. Just we are multiplying, we are splitting into two integrals. First integral d square f by dx square into x into Jn of px dx. The second integral 1 by x into df by dx into x into Jn of px dx. So x in the numerator and x in the denominator get cancelled. So you will get integral 0 to a df by dx Jn of px dx, right? That is equation number 1. We know that Henkel transformation of df by dx, which is equal to p by 2n into minus n plus 1 h n minus 1 of f of x plus n minus 1 into h n plus 1 of f of x. So replacing f by df by dx. So here we will get hn of d by dx of replacing f by df by dx. So d into df by dx, which is equal to p by 2n minus n plus 1 h n minus 1 of f. So f is replaced by df by dx. So plus n minus 1 into h n plus 1 of, again f is replaced by df by dx. So therefore hn of d square f by dx square, which is equal to p by 2n minus n plus 1 h n minus 1 of df by dx plus n minus 1 h n plus 1 of df by dx. That is the equation number 2. We know the recurrence formula 2n Jn of x, which is equal to x into Jn minus 1 of x plus Jn plus 1 of x. So here we are going to replace x by px, so you will get 2n Jn of px, which is equal to px into Jn minus 1 of px plus Jn plus 1 of px. This implies Jn of px, which is equal to, so divided both side by 2n. So 2n by 2n, right, get cancelled. On the left hand side you will get Jn of px, which is equal to px by 2n Jn minus 1 of px plus Jn plus 1 of px. Now integral 0 to a df by dx Jn of px dx, which is equal to integral 0 to a df by dx px by 2n. We are replacing Jn of px by 2n Jn minus 1 of px plus Jn plus 1 of bx dx, which is equal to p by 2n, which is a constant. Take it outside from the integration. So 0 to a integral df by dx x into Jn minus 1 of px dx plus, we are splitting the integration also. So again p by 2n integral 0 to a df by dx x into Jn plus 1 of px dx. So p by 2n is common for the both integrations. So p by 2n into integral 0 to a df by dx x into Jn minus 1 of px dx plus integral 0 to a df by dx x into Jn plus 1 of px dx. Therefore integral 0 to a df by dx Jn of px dx, which is equal to p by 2n. So first term integral 0 to a df by dx x into Jn minus 1 of px dx is nothing but hn minus 1 of df by dx. We know hn of f of x is integral 0 to a hn of f of x, right, which is equal to integral 0 to a f of x x into Jn px dx, right. Here we are having, instead of f of x, you are having df by dx. instead of jn you are having jn minus 1. Therefore this is hn minus 1 of df by dx. Plus similarly for the second term you are having jn plus 1, right? So plus hn plus 1 df by dx. Using 2 and 3 in equation 1 we will get hn of d square f by dx square plus 1 by x df dx is equal to p by 2n minus n plus 1 hn minus 1 df by dx plus n minus 1 hn plus 1 df by dx plus p by 2n hn minus 1 df by dx plus hn plus 1 df by dx. So we are removing the all brackets. So p by 2n is common for all. So take it outside. P by 2n. First term minus n into hn minus 1 of df by dx. Then minus 1 into hn minus 1 of df by dx. That is minus hn minus 1 of df by dx. Next term n into hn plus 1 of df by dx minus 1 into hn plus 1 of df by dx, that is minus hn plus 1 of df by dx. Then plus hn minus 1 of df by dx plus last term hn plus 1 of df by dx. So here minus hn minus 1 df by dx plus hn minus 1 df dx get cancelled. Similarly minus hn plus 1 df dx plus hn plus 1 df dx get cancelled. So remaining you are having p by 2n minus n hn minus 1 df by dx plus n into hn plus 1 of df by dx. Taking n outside because common. So pn by 2n minus hn minus 1 df by dx plus hn plus 1 df by dx. So n in the numerator and denominator get cancelled. So you will get Henkel transformation hn of d square f by dx square plus 1 by x df by dx, which is equal to p by 2 minus hn minus 1 of df by dx plus hn plus 1 of df by dx. Thanks.